Hello and welcome to the course Design Borefields with Confidence. This is the first chapter of the 7th part of this course, and we'll be talking about fluid temperatures inside of GHEtool. Now, we already talked quite a lot about temperature profiles. We introduced them already in part 2, and there we were mentioning that it was the average fluid temperature. Now, historically, most temperatures used in borefield design are average fluid temperatures, meaning it's the average between the inlet temperature of your borefield, the fluid going into it, and the temperature of the fluid coming out of it. Now, let us reason a little bit or recap how these fluid temperatures are actually derived, where they come from. Because when you're simulating geothermal borefields, the first thing that happens is you calculate the borehole wall temperature. And this you do with the concept of G functions. Recall the long-term effect of the temperature of your actual borehole wall. So based on the energy you inject and extract, there is a temperature drift over the seasons and over the years. And you first calculate these G functions and then what the borehole wall temperature will be in every month or at every hour. Secondly, what you do is you calculate the effective borehole thermal resistance. Now, this borehole resistance, if you recall, it tells us something about the relationship between the fluid circulating through our borefield and this borehole wall. And basically, it's a measure of how good your fluid can exchange heat with the ground, and it depends on the number of tubes you have, which type of heat exchanger you have installed in your borehole, the type of antifreeze, the flow rate, whether it's turbulent or not, and so forth. And given this effective borehole thermal resistance and the borehole wall temperature, what we can actually calculate is the average fluid temperature. Because our borehole resistance expresses the relationship between our borehole wall temperature and our average fluid temperature circulating through our borefield. But there is a fourth relationship we can now use. And that's that the in and the outlet temperature, we can also calculate this because we know the flow rate in your geothermal system. Either it's constant or you work with a variable flow rate inside of GHEtool. But basically we have this formula here that expresses that the power exchanged, that it's equal to the mass flow rate through a system multiplied by the specific heat capacity, which we know. It's a given at every temperature, and since you know the fluid you're working with, you also know the specific heat capacity, and this multiplied by the temperature difference between the in and the outlet. So let's say you have a specific flow rate and a specific heat capacity, and the difference between your in and your outlet is 2 degrees, and you keep everything the same and make it 4 degrees, you will have delivered twice as much power, twice as much energy to the ground. So since we know both the average fluid temperature and we also know the flow rate, we know the temperature difference between the in and the outlet, and we can hence also calculate now the in and the outlet temperatures of your geothermal system. Now, let's discuss why that can be interesting for your particular situation. So as said, historically, typically the average fluid temperature is used, the average between the borefield inlet and outlet temperature. And this is because it's quite straightforward that the relationship with the effective borehole thermal resistance is straight, it's linear. On the other hand, you have the inlet temperature, and it's the fluid going into the borefield. And it's what you could call the worst case situation, because let's say you're extracting heat from your borefield, so the fluid comes out of your borefield, goes into the heat pump, and the heat pump takes away part of the energy, so the fluid cools down, and it gets injected into the ground when it's actually the coolest. So right after the heat pump, it goes into the ground when the fluid is at its coldest. And the same during injection when we're cooling, and the fluid comes out of the ground, the heat gets transferred to it, it warms up, cools down the building or the process, and this warmer fluid goes back into the ground. So basically, when you're talking about the inlet temperatures, these are the worst case temperatures. They're always the coldest during extraction, heating, and the warmest during cooling or injection. And why does that matter? It's because if you want to put very strict temperature limits on your system, you want to, for example, make sure that there is no freezing anywhere, you actually have to put these limits on the inlet temperature. Because if your inlet temperature is always above 0, you know that you have covered the worst case situation. So it's basically the safest way to design. And that's also why some legislation, for example, in the Netherlands or in Belgium, for example, has to do with the injection temperature, the temperature going into the borefield, the inlet temperature. On the other hand, you also have the outlet temperature, the temperature coming out of the borefield. And this is then what you can call the best case temperature, because it's always the warmest when you're extracting heat, because your cold fluid goes into the ground, heats up again, and it comes back warmer. And the same when you're cooling with your system, your warm fluid gets into the borefield, it gives away part of its heat, and it will return colder. So the temperatures coming out of your borefield are always the best case situation, let's say. Now, why is this temperature potentially interesting for you? It's because the rated power for heat pumps is typically defined as the fluid coming into it. And the fluid entering the evaporator of your heat pump, that's the same fluid temperature that also comes out of your borefield. So the borefield outlet temperature is exactly equal to the fluid going into your heat pump. And if you, for example, are designing your system to make sure that, let's say, your inlet temperature is always positive, so your inlet temperature is above 0 degrees, it can happen that your outlet temperature, the worst case, the coldest outlet temperature is 3 degrees, let's say. And then you know that, given that you have to select a heat pump that with 3 degrees can deliver the power required to your building. And that's how these 3 different temperatures can each give you different insights. And also when we're going to the next chapters and talking about required borefield size and borefield depth, it's important to think, am I caring about the average temperature and the traditional way of designing systems, or do I actually want to reason with the inlet or the outlet temperature? Because that will change the required borefield size, because the temperatures are, as said here, either an average or the best or the worst case. Now let's us jump into GHEtool and show real quick how you can switch between these temperatures and what exactly the difference can be. So here we are in GHEtool Cloud. I created a new project for you, and let's discuss now how you can use inlet and outlet temperatures inside of your project. So here over in the simulation settings, you have, it's a very recent update, so in the beginning of this course it was not yet there, but now it is, the feature or the option to select average inlet or outlet temperature. And what is important is that when you change it here in the simulation settings, not only your minimum and maximum thresholds are going to change to inlet or outlet temperature, but also every other fluid temperature in the graphs as well. So let's start with average. First, the situation we're going to simulate has 4 boreholes, and for the borehole resistance it's a W, monopropylene glycol, and we will work with a variable flow rate with a fixed temperature difference of 3 degrees between the inlet and the outlet. So if you recall, having here a constant temperature difference means that the flow rate will be updated in every month during heating and cooling separately. When we go to the thermal demand tab, what you can see is that we will be working with a monthly load profile with our standard distribution. And if we now go to the results, you can see that we have here our temperature profile, and we're familiar with that. These are the average fluid temperatures. And as you can see, we go down to what's the minimum temperature here, around 0.5 degrees Celsius. So this is with the average fluid temperature between the inlet and the outlet. Now let's us rename this scenario to average, shall we? And then we can duplicate it and now do the same with the inlet temperature. So for that, let's go to General tab, select here the inlet temperature, calculate it, and now everything will be automatically converted to working with inlet temperatures. And what you see here is exactly what we discussed. It's now a very worst case situation. It's now not anymore almost 0.5 degrees Celsius, but it's now -1 degrees. And that's because, as we said, the temperature going into the bore field is always the coldest one. So it's colder than the average one. But also, as you can see here, the maximum fluid limit is now 17.6. And with the average one, it was 16. Because so here, when we're injecting heat, the inlet temperature is also the worst case situation. Now, to end, let us do the same simulation again, but now with the outlet temperature. So if you go back to general and select here the outlet temperature, it will again do the same simulation, now not with the inlet but the outlet. And here you see that we have the best case. So in extraction, we're now at almost 2 degrees Celsius. So by far the furthest away from a limit from all the 3 different cases. And also during cooling, and when we're injecting heat into the ground, our maximum temperature is now only 14.6 degrees Celsius, where it was 16.13 in the average case. Now, before we wrap up this, I want to draw your attention to one very specific detail. Namely, we see that the average is 0.48, the inlet was minus 1.02, and the outlet was 1.98. This means that the difference between the inlet and the outlet temperature is exactly 3 degrees Celsius. And that's the same temperature difference we explicitly set here. So this means that when you're working with a constant temperature difference between the inlet and the outlet, there is a very clear relationship between the average inlet and outlet temperature. However, if you're working with a constant flow rate, this will vary, because then your flow rate is constant and your delta T will vary in heating and cooling from month to month. So I hope you found this chapter already interesting. You remember or you take away that there are different fluid temperatures you can actually work with or design with. And using that information, let us now talk about how you can calculate the required depth for your boreholes in order to make sure that your temperatures stay within the limits you set up.